Hello to you all. In this session, I want to talk about capacitors that you have surely seen a lot. In electronic circuits, you can see that these are also known as microcapacitors, and they are usually made for high voltages. For example, you can see that this capacitor is labeled 250 volts, and this one, for instance, is 400 volts. We want to see what these capacitors actually do in electronic circuits and what their applications are. For example, here, where this is an electronic protection board, this very power protector, you can see that a capacitor is placed at its input. If you look closely here, you'll see that this is the input voltage where the capacitor is placed in series, and there's also a resistor underneath it. But for now, we're focusing on the capacitor, or in power circuits, as we can see here in this power supply. This is a computer power supply, and you can see that these same types of capacitors are used inside the power supply. Well, since these capacitors are mostly used in circuits like surge protectors, and they're used quite a lot. Maybe a lot of people think that this capacitor is used to reduce voltage, but is that really the case? Does the voltage that enters this capacitor actually decrease? Let's test it with a multimeter and see. So, I've brought a multimeter here, and now we're going to run some tests to see how it works. First of all, let's start. We're going to check and test the input voltage to the capacitor and see what happens. I have a wire here with alligator clips on both ends, and one end is connected to a power plug. First, we want to test the capacitor to see if it actually reduces the voltage or not, so let's set the multimeter to model. We set it to AC mode because our electricity is alternating current, and then we connect it to the multimeter. Okay, one side, which is neutral, gets connected to the neutral, and the phase, which we're going to test through the capacitor. To keep the capacitor from moving and for safety, I place it on the breadboard. I connect one end of the wire, which will be the phase, to the capacitor, like this, and with the other probe of the multimeter, I perform the test. That means now I've placed the capacitor in the path of the wire, and then I proceed. I plug the two-prong plug into the power outlet. Now I've plugged it in, so now I start testing. As you can see, the capacitor is showing me about 220 volts. So it hasn't reduced the voltage at all. Look, if I measure the voltage from this part as well, meaning before it enters the capacitor, you can see that I have 220 volts, and if I measure the voltage after the capacitor, I still have 220 volts. So what is this capacitor doing here? What does this capacitor do in the telecommunication circuit? If it doesn't reduce the voltage, then why is it being used? Let's examine this together. Well, it's the same with this capacitor. If I want to test this one as well, it will give me the same output. Let's go so I can first give you the explanations, and then we'll come back to do the final tests as well. Alright, pay attention to this chart and this image, this chart that you see here. This is actually a form of AC voltage, or in other words, AC voltage. We move along the timeline like this. Now if we take this voltage, whether it's 220 volts or 110 volts, and apply it to one side of a capacitor, specifically this type of capacitor will have the same output voltage on the other side as well. That means the voltage doesn't decrease. Whether it's this type or that type, it doesn't make a difference. The structure of these capacitors is almost the same, and when we apply AC voltage to the capacitor according to this diagram, keep in mind that we're only talking about AC voltage. That's what we're discussing. When we apply AC voltage, we receive the same AC voltage on the other side. However, there are some differences and changes that occur, and here you can see we've introduced the resistance symbol. When AC voltage is applied to the capacitor, meaning the capacitor is placed in series in the voltage path, this is how it works. It exhibits resistive behavior and acts exactly like a resistor, as you know. And if you are well versed in electronics, you know that the function of a resistor is not to reduce voltage. Rather, the resistor limits and reduces the current or the current intensity, which is measured in amperes. Therefore, when the capacitor is in this state, it exhibits resistive behavior. In fact, it behaves somewhat like a resistor. So what does it do? It limits the current, and this is where we receive the voltage, but we won't have as much current as at the input. For example, as mentioned, you can perform this test. Say on one side it will apply 220 volts on one side, and on the other side connect a lamp that would normally light up directly with 220 volts. You will see that the lamp does not turn on, while if you connect this lamp directly to 220 volts, it lights up. Why doesn't it light up here? Because the capacitor doesn't allow enough current to reach the lamp, because in this circuit it behaves like a resistor. As a result, the lamp doesn't turn on, and this is the behavior and function we're talking about. This is also called the capacitive reactance of the capacitor, which is the resistive behavior of the capacitor, as it's written here as well. Limitation of electric current, which is now completely clear. This is the reason why when we want to apply voltage from this side, we only receive the voltage, but there's another point to consider. Well, it's that we can reduce this voltage and use the limited current to generate voltage again and proceed. We can use the voltage generated from the limited current in various ways, and we can design a circuit that reduces the same 220 volts or 110 volts voltage down to ranges like 12 volts, 15 volts, or even 9 volts, 5 volts, so that we can use this voltage for different circuits. And that's why the capacitor you see is present and used in many circuits. Now that you've understood how a capacitor behaves with DC voltage and AC voltage, and what it actually does, why it didn't reduce the voltage, and what its role is in these circuits, in the following will also work more practically. As mentioned, this is a power protection circuit. Well, as you noticed, the capacitor, in this mode, the capacitor exhibits a resistive behavior against the current intensity. And it acts like a resistor. In other words, it doesn't reduce the voltage, but it severely limits the current. For example, if you connect a lamp directly to this 220 volt voltage, the lamp will light up. But if you place this capacitor, just as I have positioned it, in series with the voltage and then connect the lamp to the other side of it, you will see that the lamp does not light up. You can easily test this right now with any lamp you use. Whether it's an LED or an incandescent bulb, you'll notice that the lamp either doesn't turn on at all, or if it does, it will be extremely dim. This means that the current is severely limited. When we reduce the current, what else can we do? We can also limit the voltage, and using a voltage divider circuit, reduce the voltage as well. For example, in this sample circuit, we have an IC that is responsible for control, along with other components. For instance, here we have a capacitor that is 30 volts, and another capacitor that is 10 volts. But while we have a 220 volt input here, how is it that these 10 or 20 volt capacitors don't get damaged? And this IC, whose maximum operating voltage is 15 or 16 volts, how does it not get damaged either? This is where, by using this capacitor, we pass the 220 volt AC mains voltage through the capacitor. The voltage doesn't decrease, but the current is significantly reduced. Then we feed this electric current, whose amperage and flow have been reduced, into a diode circuit. That will be our bridge rectifier, where the current is converted to DC. But before entering the diodes, by using several resistors, which you can see here, we perform a kind of voltage division and set up a voltage divider circuit. We'll make separate videos about voltage divider circuits later, but these circuits allow the voltage to be significantly reduced. Reduced without creating a short circuit between positive and negative, or phase and neutral, which is made possible by the resistors. So when we limit the current, we can also reduce and limit the voltage at the same time. And we take this AC voltage, which has been divided and reduced by the voltage divider circuit, and feed it into the bridge rectifier so it can be converted to DC. You see here that there are 4 diodes, but the other diodes also serve different purposes. So it's not just 4 diodes, but the 4 diodes are specifically for the bridge rectifier, so that we can fully convert it to DC, and then we can use this DC power. We can supply it to the IC, capacitors, and other components so they don't burn out or run into problems. For example, as you know, these LEDs operate at 3.3 to 5 volts. That is, if you give it more voltage than that, it will burn out, but as you can see, it's easily placed in this circuit. So this means that the voltage has been properly reduced and it's working. Now let me show you this same voltage divider circuit in practice so you can see how it works. First of all, I built it on a breadboard, but before I explain it on the breadboard, to make it easier for you, let's first take a look at its diagram so you can see how the voltage divider works. Here you can see a simple voltage divider circuit. You can see it here on the left side. We have 2 resistors, R1 and R2, and you can see that from the middle of resistors R1 and R2, we also have the output on this side, which is labeled Vout, and that's actually our output voltage, while this side is VIN, or the input voltage. This is a very simple voltage divider circuit, which can of course be built with more resistors as well. But to explain how it works, I'll stick to this simple circuit. You can see that this way we can perform voltage division. For example, let's say we have 200 volts at the VIN section. It depends on the type of resistor and the resistance value we choose. At the output or the Vout section, we might have different parallel voltages, for example 100 volts, 50 volts, and similar voltages. So what did we do and how did we do it? Do we use voltage division in circuits like protection circuits or other circuits? We place the capacitor in the voltage divider circuit like this, and we see that the only change that has happened is that the capacitor has replaced this wired section and the voltage comes through. It passes through the capacitor, enters the voltage divider circuit, and in the end we will have volt again. Here, because it behaves resistively, it reduces the current. In the voltage divider circuit, due to the resistors, we will again have a different current. And as a result, in this section, we will have an output voltage, which I'll repeat again. Depending on the resistance values, it can vary, and by using the formula and changing the resistance values and choosing the right resistors, we can create our desired voltage here. Then our desired voltage, which here is in the form of AC, is given to the diode bridge, and by the diode bridge, it is converted into DC voltage. After that, we can use that DC voltage, which has a suitable current for operation, for circuits such as ICs, LEDs, and protection circuits. We use it, and the overall behavior and structure of our voltage divider circuit is based on capacitors and resistors. In fact, right now you have the structure of a very simple power circuit. You can see now that you have become familiar with the voltage divider circuit. As a final note, now that we are going to test this circuit in the next steps, we connect the negative probe or the neutral to this part. On the multimeter, we connect the positive probe to this section as well, and in this way, we measure the voltage. Now, if we want to use a diode bridge, we place it here. That is, it's as if this is our AC input voltage that has been reduced, and now we feed it into the diode bridge. Now, since we place the diodes after this, we can use the multimeter we can test them using the DC test mode and then use them. Now, with this circuit, I hope I've made it clear to you how our voltage divider circuit works here. And just like that, our voltage divider circuit operates this simply. So now that you understand how the voltage divider works, you also know how this circuit functions. For now, I've only placed 2 diodes because my goal isn't to build a complete circuit at this point. Music but incomplete circuits. Like this, there are 4 diodes that can form a diode bridge, and of course you can even use a diode bridge directly. That is the output voltage in such circuits. Meaning if you want to build such a circuit, after it passes through the voltage divider as well. You can directly connect it to a diode bridge, meaning a diode bridge IC, like the example you see here in this image. But now, since the goal is educational, we want to get familiar with it. You can see that here I have placed a voltage divider circuit. I take this resistor, I place it here like this. If you pay attention, this capacitor is paralleled with a resistor. Why is it paralleled here? If you notice, this is also the case in some other circuits. There is a resistor under the capacitor that is in parallel with the capacitor. The function of this resistor is to discharge the capacitor. You know that if we connect voltage to the capacitor, and if the capacitor isn't discharged, it might cause an electric shock if touched, or in general create an electrical hazard. It could deliver a strong shock and be dangerous, or the electricity could remain in the circuit. But we want, when the circuit is turned off, especially in such circuits, we want the capacitors to be discharged. Especially this capacitor, which has a high voltage, it should be discharged so that no voltage remains in it. Well, this is what this resistor does, which is why they use a resistor in the protector. As you can see, the voltage that enters from here, from the point where the voltage comes in, passes through the capacitor, and well, its current drops significantly, but it still has the same 220 volts afterward. It then passes through these bridge diodes and is converted to DC. But before it gets converted to DC and enters the bridge diodes, its voltage is still high. And naturally, from this point as well, we will receive a higher voltage, but what we want is for the voltage to be reduced, and we don't want to get, for example, that same 220 volts as DC output. So here I've placed a series of resistors, and now which resistor to use here to get what voltage at the output is a completely separate issue and has its own specific formula, which we'll try to cover in another video. But we have a course called Electromechanics. It's explained from the basics there, along with resistor calculations, and it's available for free on our YouTube channel, and you can watch it there. But we also try to release various other videos cheap as well. So here we've created a voltage divider circuit using 2 resistors. For example, if I connect the phase to this terminal and the neutral to this pin, since part of the voltage returns to the neutral through the resistors, and it goes back to the neutral, so you could say it's lost and both the voltage and current decrease. As a result, we'll have a lower voltage here, and this way we can reduce the voltage. Now let's go ahead and see this in practice as well. Alright, so again I take the wire. One side is phase, or it could be neutral, that I connect here, but before I use the voltage divider, because my goal is to see how high the voltage will be here. For now, I'm taking the DC voltage directly from the capacitor itself and measuring it straight from the capacitor using the multimeter. I'll turn it on and set it to DC mode this time because I want to test it after the diode, without using the voltage divider circuit. I'm testing it after the diode, and let's see what voltage it shows us. As you can see, it's showing about 98 volts. It's showing us this, although the diode and the capacitor themselves, because the current has been reduced as a result, the voltage has also dropped significantly. You see, it's dropped from 220 volts to 95 volts with this, and that's a significant reduction. This is because the capacitor, by limiting the current, has also limited the voltage, and we've converted this current back into voltage. But here, even this roughly 100 volts that we have is still too much for my circuit. We want to bring the voltage down to below 20 volts, even around 12 or 13 volts. This is where the voltage divider circuit comes into play. So to use the voltage divider circuit, what do we do this time? We connect the neutral to this section, to this junction. The resistors here, as you can see, are separated from the capacitor and act as the neutral. We connect it here. You see, the phase is connected to the input of the capacitor, and the neutral is connected here. And in order to be able to measure, well, we still need to connect the multimeter to the neutral so that our multimeter also has its neutral. That's right, so it can measure, but here, now we have the neutral, and now again the phase, which is also in DC form. Actually, does the phase become neutral here? I explained this in the video. Because we're measuring from DC, I'll power the circuit again, and this time let's see. With the voltage division that has occurred, how much our voltage has dropped, and well, we'll take our measurement. We see that the voltage hasn't changed much. But of course, we can lower the voltage further by changing the resistance values and the position of the voltage divider circuit. For example, here this time I connect this neutral side to the next terminal of the resistor, which is closer to the neutral in the circuit. I connect it and place the multimeter again. I connect it to the power to see what voltage I get this time. So I measure the voltage, and we see that the voltage has dropped by another 10, maybe even more, about 10 or 12 volts less, and this time it's around 8.8 volts that it's showing us. Now we want to lower the voltage even further, as much as possible, as I mentioned. It's not just random, there's a specific formula for it. Our goal here is only to the position of this capacitor. You can see that up to this point we've managed to bring the voltage down to 8.8 volts. Alright, here I replace the resistor. This is another resistor, and I substitute this resistor in its place. It's about 22 kilo ohms, and here again I calibrate the multimeter. I connect this voltage divider circuit and the circuit back to the board, and again I measure the voltage. As you can see, our voltage dropped to 47 volts, that is below 50 volts, and we were able to do it quite easily. With a simple voltage divider circuit, we kept lowering the voltage. And as mentioned, if you do the calculations and use resistors with the correct wattage and especially the right resistance value, you can very easily set the voltage to your desired value. For example, for this circuit, if you need 12 volts, you can bring the voltage down to 12 volts, and this voltage is sufficient for us to be able to circuits that require 12.3 volts, so that we can build such circuits. And as you can see, with a very simple voltage divider, we were able to have a power supply circuit. And in fact, the main goal of this lesson was for you to understand the reason for the presence of this capacitor. And now you fully understand what these capacitors are used for and why they are included in circuits. Next comes the number of resistors and then the music diode. In fact, this capacitor, along with the resistors that are here, works to perform the voltage division, and with the diodes that are present here. They create a good power supply circuit with suitable efficiency for circuits like this, for example, a power protector. And the advantage of this power supply circuit is that whenever the power is switched on and off under high voltage, it suffers less damage. That's why in circuits and power protectors like this, several types of power supply circuits are used. Otherwise, well, they could also, for example, use a switching power supply circuit in these circuits. But that's really not the right thing to do, because switching circuits themselves are immediately damaged when the power is switched on and off. But this circuit is of the linear type and is based on a transformer and resistor, which has a very long lifespan, and its accuracy is always maintained. The point I wanted to tell you is this. Well, now in the construction of several circuits, usually resistors with a 5% tolerance are used, but if you want to maintain very high accuracy and have more precise circuits, you can use resistors with a 1% tolerance. Oh, our calculations remain the same, but the type of resistor, now you can tell from its color. It's clear that it's a 5% tolerance, but if it's a 1% tolerance, which usually it's this color, you should use it. Well, naturally, you'll get a better output. I hope this video was useful for you, and until the next session, goodbye.